This lesson will teach you about the nature and causes of wind shear, including its extreme form known as microburst, its effects on aircraft, and the operational procedures that you will need to know to avoid or counteract those effects. Wind shear is a meteorological phenomenon that can occur normally anywhere in the atmosphere up to the tropopause. It can be defined as an abrupt or localized change of wind velocity, that is, strength, direction, or both. It can occur both vertically and horizontally. As a pilot, you will need to be familiar both with the situations in which you could encounter wind shear and the actions you would need to take to recover safely. The greatest potential risk posed by wind shear to aircraft of any size or type happens at low level and low speed, where an aircraft is vulnerable during initial climb and approach to land. In particular, on the approach, the aircraft is at low level, low speed and low power, and because of that it has a relatively low total energy to overcome potential problems. There can be several causes of low-level wind shear. The first we shall look at is the passage of a front, in which the isobars change direction and thus often become more widely or more closely spaced, giving not only a change in direction, but also a change in speed. Generally speaking, these changes are fairly gradual, but a deep depression with strong winds can produce significant wind shear. A marked temperature inversion can also give rise to wind shear. Below the inversion, the wind will be affected by surface friction, and will thus back and decrease. It may also become turbulent if there are significant obstacles. Above the inversion, the wind is unaffected by these changes to the surface boundary layer. To an aircraft flying at low level, topography and large buildings can have significant effects on the wind. Hills and buildings will cause mechanical turbulence, which causes gusts, but these are usually of short duration. Surface friction will also cause changes of wind speed close to the ground. By far the most dangerous form of wind shear is that which is generated by cumulonimbus clouds, often known as Q-nimbs, and their associated weather of heavy rain and hail, which can give rise to the phenomena known as microburst, and its bigger brother, macroburst. A microburst is generally accepted to be about 5 kilometers across and of about 5 minutes duration, although gusts and wind shear can be encountered up to 20 miles from the thunderstorm. The downdrafts generated can be very strong. Over 6,000 feet per minute has been recorded, and can often exceed the rate of climb of many aircraft, particularly in low speed and power situations as on the approach, and the changes of wind direction and speed are large and sudden. Microbursts have caused several fatal accidents involving airliners and light aircraft. All pilots should treat Q-nimbs with great respect. The following sequence of diagrams will help to explain what will happen to an aircraft as it flies through a microburst on the approach to an airfield. First, the aircraft will meet a sudden increase of headwind, which will cause an increase in airspeed and a decrease in rate of descent, a gain of energy which takes the aircraft above the desired approach path. The pilot reduces power to regain the desired approach path, and also possibly to prevent exceeding gear or flat limits. The rate of descent increases, and at the same time the aircraft enters a reducing headwind and increasing downdraft, a loss of energy which leads to reduced airspeed, less lift, and an even greater rate of descent. As the aircraft continues, the outflow from the microburst is now coming from behind, and the increasing tailwind reduces the airspeed even more, accompanied by an increase in the descent rate. The pilot's problems are added to by the effect of vertical wind shear and the strong downdrafts, which can cause further variations in speed and rate of descent. You can deduce from this sequence that, no matter what type of aircraft you are flying, a microburst is a very serious hazard, and if the correct recovery action is not carried out promptly, the result could be at best frightening and at worst disastrous. It is best then to avoid the hazard rather than have to recover from it. The likelihood of serious wind shear can be ascertained at the flight planning stage by careful checking of weather forecasts, looking in the significant weather charts and terminal aerodrome forecasts, or TAFs, for key symbols and acronyms, such as MTW, mountain waves, TS, thunderstorms, GR, hail from the French grêle, RA, rain, SH, showers, a plus sign indicating heavy, and CB, cumulonimbus. Note that some of these codes can appear in combination. If at any stage of flight any moderate or severe turbulence, wind shear or microburst is encountered, air traffic control must be informed with details of location and severity of the phenomena to allow them to issue warnings to other aircraft. Ultimately, awareness of the phenomena, which may or not be visible, must be backed up with prompt and positive action should you find yourself experiencing the conditions caused by a microburst or wind shear. If the speed increases suddenly, resist the temptation to decrease power, as the effect will probably be short-lived and will probably be followed by an opposite effect. It would be better to disregard the glide path and raise the nose to control any excessive speed. If the speed reduces and rate of descent increases, set full power and adjust attitude, maintaining configuration and a safe margin of speed in case of further speed losses. If necessary, pitch to the onset of the stick shaker if fitted. It is safer to discontinue a destabilized approach than to try and re-establish stability in increasingly dangerous conditions. The same procedure can be used in the initial climb after takeoff. This lesson has described several sets of weather conditions and situations that can give rise to wind shear, the most hazardous being the cumulonimbus. Remember, Q-nim clouds and thunderstorms have huge amounts of energy, capable of generating many hazards. Severe turbulence, hail, lightning, and more, including microbursts with rates of descent in downdrafts, which can far exceed your aeroplane's rate of climb. Avoidance is the preferred option, but if needed, a successful recovery will depend on a pilot's anticipation and skill, and on adequate reserves of power, height, and speed.